For this particular video, I'm going to show you how to solve some strong titration problems. So these are the steps you would need to follow in order to be able to do one of these problems. Okay, so before we begin one of these problems, it's very important to understand the intervals that they could actually ask you to calculate the pH for. So as you can see for this particular example, NaOH is being added to HCl, so a strong base is being added to a strong acid. The NaOH would be in the burette itself, and the HCl would be in the flask. So they could actually have you calculate the initial pH of just the acid itself in the flask. You could be asked then to calculate the pH at any point from when you first start adding the NaOH up to the equivalence point. So there would be some acids still remaining there. They could actually ask you something about the equivalence point itself. Obviously, because this is a strong acid, strong base type problem, the pH at the equivalence point is going to be 7, but they could easily ask you how many milliliters of NaOH you would need to add to reach that point of where the moles of acid equal moles of base. Or they could ask you to calculate the pH after the equivalence point, which in this case, the acid would be completely neutralized and you would have only the OH minus to worry about. So it's important to understand these different intervals and how to go about solving for each particular part. This is just a summary of what to do for each of those intervals before I actually guide you through one of the problems. If they ask you to calculate the pH initially, you just take the negative log of the concentration of the analyte. These are strong acids or strong bases, so they're 100% associated. So if you know the concentration of the H plus or the OH minus, you can quickly find the pH. At the equivalence point, the pH for a strong problem is always going to be 7. And at any other point, all you have to do is figure out the moles of acid, the moles of base, subtract the two, and then determine the concentration of whichever there is more of and use that to determine pH. I know that's kind of summarizing a lot there, but I'll show you how to do this in one of the problems. Also important to understand these graphs. If this is a strong problem, you know that the pH in this case, this would be a strong base being added to a strong acid, as you can see in the picture. Initially, the pH is pretty low. It doesn't change much at first, and then it quickly jumps up at the equivalence point. And the pH at the equivalence point is always going to be 7 for a strong problem. And then it will slowly kind of level off there. So this is what you would expect to see for a strong acid, strong base titration. So now I'm going to guide you through how to solve this particular problem. As you can see here, they're asking you to find the pH when the following quantities of 0.10 molar nitric acid has been added to 25 milliliters of 0.10 molar KOH solution. So for the first one, they want you to find after 24 milliliters of the acid has been added. Very important when you're doing a titration problem to actually write the equation first. So for this particular neutralization reaction, we have nitric acid reacting with potassium hydroxide. This is a neutralization reaction, so it's a forward arrow. And remember, you always end up getting a salt plus water for a neutralization reaction. So that's the particular reaction that we are actually doing here. Notice everything's in a 1-to-1 ratio, so that'll actually help us later on when we're solving this problem. So this particular problem is a strong base being titrated here with a strong acid. Okay, so the base itself would be in the flask and the acid would be in the burette, and you're adding it to the base. So the first thing we need to do here in order to figure this out, we have to figure out how many moles of base we actually started with here. So in this particular problem, there's 25 milliliters of the KOH, and we can convert that to liters here. All right, there's 1,000 mils for every liter. Our milliliters cancel. and then we know the concentration of the KOH. There's 0.10 moles of KOH for every liter. Liters cancel. Now I know how many moles of KOH I initially started with here. So it's 0.0025 moles of my base, my KOH, that I'm starting with. I like to label these things as I go through, just so that keeping myself organized, as some of these problems can be pretty long. So this would be the moles of base that I started with. So if I'm adding 24 milliliters of the acid, now I have to figure out here how many moles of acid I'm actually adding to this. Because remember, this is a neutralization reaction. I have a certain amount of base, I'm adding acid to it. As that acid is added, it's attacking the base and essentially neutralizing it. So I have 24 milliliters of acid. Convert that to liters here. And now that I'm in liters, I can use the concentration. I know that the acid is 0.10 molar, so there's 0.10 moles of the nitric acid for every liter. And from that, I know that there's 0.0024 moles of my nitric acid that I added. Again, I like to label this so that I can keep my self going here and not messing up these problems. So I started with 0.0025 moles of KOH. I added 0.0024 moles of acid. So essentially here, think about what's actually taking place. Remember, from this particular reaction, this is a 1-to-1 ratio. Okay, so if I'm adding that many moles of acid, I am destroying the same amount of base. So as I keep going here, I know that I started with 0.0025 moles of the base. I added 0.0024 moles of the acid. Okay, so essentially what's happening is the base is destroying that acid. We haven't reached the equivalence point yet, so the base is essentially still winning out. So when this reaction is said and done, I have 0.0001 moles of the base, the KOH, still left over. Okay, because I didn't add enough acid yet to neutralize all of the base that was present. So if I still have 0.0001 moles of the base left, it's now floating in, though, a total of 49.0 milliliters of solution. Remember, I started with 25 milliliters initially, and I added 24 milliliters of the acid. So my new volume at this point is 49 milliliters. So if I want to figure out the concentration of the base still remaining, I can convert this quickly. 1,000 milliliters for every liter. Now I'm in moles per liter. Okay, I know the concentration of the base left over here is 0.002 molar. And remember, this is KOH, which is a strong base, so it's going to dissociate 100%. Okay, so that means if I know the concentration of the KOH, I now know that this is the concentration of the OH minus because it's a 1-to-1 ratio. So now that I know the concentration of the OH minus, the POH is equal to the negative log of the concentration of OH minus. So the negative log of 0.002, which would be equal to 2.7. Remember, we only had one sig fig here, so we only want one decimal place in our pH. And this is POH, so pH plus POH we know is equal to 14. So 14 minus the 2.7 would give us the pH of 11.3. This should make sense. We haven't reached the equivalence point yet. Remember, at the equivalence point, it would be a pH of 7. We have added some acid here, but the base still remains, so we would expect a more basic pH for at least part A. So now to calculate part B here, after 27 milliliters of the acid was added, again, I need to figure out how many moles of acid I added here to the base. So I added 27 milliliters. I got to get that to liters so I can use my concentration. There's 1,000 mils for every liter. And I know that there's 0.10 moles of nitric acid for every liter according to the concentration. And from this, I know that there's 0.0027 moles of the nitric acid were added here. Okay, there is no need to calculate the amount of base that we started with. It's the same as we already calculated in part A, so there's no reason to do that again. Again, still a 1-to-1 ratio here. So because of that, we know that in this case, we now added more acid than there was base present. So we added 0.0027 moles of acid. There was only 0.0025 moles of base. This was the base we started with here that we calculated in part A. Okay, so essentially what happens is all that base reacts with the acid, but the base is essentially being used up. It's a 1-to-1 ratio. There's only 0.0025 moles of base available to react with the acid. So that allows us to subtract here and see that there's only going to be 0.0002 moles of acid left over here. So when this neutralization reaction takes place, all the base has been neutralized. We are past the equivalence point here, and we have actually added extra acid, 0.0002 moles extra. So when this reaction is done, there's 0.0002 moles of the HNO3 flowing around now in 52 milliliters of solution. Remember, we started with 25 milliliters. We added 27 milliliters. 25 plus 27 gives me 52. We can quickly convert this. There's 1,000 milliliters for every liter. This gives me the concentration. So my ending concentration here would be 0.004 molar. This would be for the nitric acid, but remember, this is a strong acid, so it's 100% dissociated. So if we know the concentration of the acid, it's a 1-to-1 ratio. So this is the concentration of the H plus. So if we want to find the pH of this, we know the pH is equal to the negative log of the concentration of H plus, which is equal to the negative log of the 0.004, which gives us a pH of 2.4, 1 decimal place because we only had 1 sig fig. So that's how you go about solving for this particular problem. Another problem is coming up. For this particular problem, it looks like we have a 0.10 molar solution of sodium hydroxide being put in a burette, and then using that to titrate 50 milliliters of a 0.20 molar nitric acid. So this particular problem is a strong acid being titrated with a strong base. So the acid is in the flask and the base is in the burette being added to the acid. Very important to write your reaction here. So we have sodium hydroxide, NaOH, reacting with nitric acid. This is a neutralization reaction, so we end up getting a salt plus water. And notice again, this is all 1-to-1, so this makes it very easy later on when we're doing our problem. The first part here wants us to find the initial pH of the acid solution. So remember, initially here in the flask, all you have is a strong acid. And because it's a strong acid, if you know the concentration of the acid itself and it's a 1-to-1 ratio, you know the concentration of the H plus. So pH we know is equal to the negative log of the concentration of H plus. The concentration of the acid and the concentration of the H plus is 0.20. So negative log of 0.20 here gives us a pH of 0.70. So finding the initial pH of a strong titration is pretty easy. just take the negative log of the concentration and you'll get your pH. Part B wants us to find the pH after 65 milliliters of the sodium hydroxide has been added. So remember here, this is a neutralization reaction. So when we're adding this NaOH, the acid that is there is going to react with it and neutralize it up until the point that the acid that is present is gone. So our goal here is to figure out, is there still acid left, or did we add enough base to essentially now destroy all that acid? So we're going to figure out how many moles of acid we actually started with. So we had 50 milliliters here of the acid in the beginning. So we can figure out the moles by getting to the concentration. So if we have 1,000 mils here for every liter, now that I'm in liter, I can use the concentration, which is going to allow me to get to moles. There's 0.20 moles of the nitric for every liter. Now I can see that I started with 0.010 moles of the HNO3, and this is the amount that I started with. I like to label these things. So if I added 65 milliliters of NaOH, let's see how many moles of base I actually added here. There's 1,000 mils for every liter. Now that I'm in liters, I can use my concentration to figure out the moles. In this case, though, there's 0.10 moles of the sodium hydroxide for every liter. So I actually added 0.0065 moles of the NaOH. So I can see here, okay, that I started with more acid than base that I added. So the acid is still going to win out here. I haven't been able to neutralize all of the acid. This is a 1-to-1 ratio again. Okay, so if I added that much base, I destroyed that much of the acid. So 0.010 moles of the acid I started with minus the amount of base that I added, and I actually end up having 0.0035 moles of the acid left over. Okay, I did not add enough base to neutralize all the acid. That's why I still have more acid remaining. And you can see there I messed with the sig figs a little bit. These numbers are pretty small, so I didn't want to round that up and change it. It changes the pH a little bit, but this is just a preference I had for this particular problem. Usually the numbers work out. But I decided to just go there to 4 decimal places and not cut off the number itself. So that's how many moles of acid I have left. So there's that many moles of acid now floating around in a new volume of solution. Remember, I started with 50 milliliters. I added 65 milliliters. So it's actually floating around now in 115 milliliters total. So I know there's 1,000 mils for every liter. This will allow me to calculate the concentration of the acid that I have left over here. I have 0.030 molar for the concentration of the acid. And remember, this is a strong acid, so if I know the concentration of the acid itself, this is the concentration of the H+. So this is my concentration of the H+ that is still remaining. If I want to know the pH of that, I know pH is equal to negative log of the concentration of H+. So the negative log of 0.030 is equal to 1.52. Okay, so I did not reach the equivalence point yet. So I haven't neutralized all of the acid that was there. I had some acid left over, and when I calculate the pH reflects that there's still some of that acid left over because it's a very low pH. Part C now wants me to calculate the pH after 150 milliliters of the base has been added to the acid. So I already know how many moles of acid I started with, from part B. So now I want to figure out how many moles of base I added this time. So I have 150 milliliters of base that I added. I know there's 1,000 milliliters for every liter, and I know that there's 0.10 moles of the NaOH for every liter. So in this particular case, I added 0.015 moles of the NaOH, and this is how much I added. Again, this is a 1-to-1 ratio here. As you can see, we already calculated the amount of acid we started with. This is more than the amount of acid we started with, so there's going to be base left over. So 0.015 moles of base were added. I can subtract the amount of acid that would react with this. In this case, that's the amount of acid I started with. Essentially, all of the acid is going to be neutralized. Okay, it's a 1-to-1 ratio. So if all the acid reacts with the base, there would be 0.005 moles of the base left over. Okay, so we've reached and passed the equivalence point. All of the acid is neutralized, and there is just now base remaining. So we have 0.005 moles of the base, the NaOH, floating around in a new volume of solution. We added 150 milliliters to 50 milliliters, so that's a total of 200 milliliters. I know that there's 1,000 milliliters for every liter. This will give me a concentration here of 0.025 molar, and that is equal to the concentration of OH minus. Be careful here. The acid is all gone. The only part left over is the base. It's NaOH. So if you know the concentration of NaOH, you know the concentration of OH minus. So from the concentration of OH minus, we know that the pOH is equal to the negative log of the concentration of OH minus. So the negative log of 0.025 is equal to 1.60. This is not the pH though, this is the pOH. So pH plus pOH is equal to 14. 14 minus 1.60 gives me a pH of 12.40, 2 decimal places, because we had 2 sig figs in our concentration. So that's how you go about solving the parts of this particular problem. Remember, this is specifically for a strong titration problem.